Good afternoon, hello everybody. It's my great pleasure to welcome here again Dr. Javlon Rayimbaev, coming from Uzbekistan, from National University of Uzbekistan, and he's going to tell us something during this seminar concerning testing spacetimes around astrophysical compact objects using astrophysical observations. Please.
Okay. Thank you, please. Yo, bunu o'tkazib turish kerak ekan. So I should here. Control. So it's okay. I will. Today I'm going to tell about testing the space-time around compact objects. Actually, I will talk about the black hole testing, space-time of black holes, and using the observational astrophysical observations. So I will make some brief introduction. So actually, as we told as our before lecture, and the black holes are very simple objects. Actually, they are not very simple, since they have 2 or 3 parameters, one parameters. We don't know these parameters are the parameters of space-time around the black hole, not actually black hole itself. So what is black hole? Is there some exact matter inside the horizon? We don't exactly know. We don't know about the inside the horizon. So we will work on with space-time around black hole. So in this, from mathematical point of view, these black holes are solution of gravitational field equation. So for the first time, this Einstein field equation, the solution of Einstein's field equation has been found by Karl Schwarzschild, and at the same year by Reisner. So for point like spherical symmetric black hole, but in Reisner-Nordström they include the field equation Lagrangian density, so electromagnetic field density, Lagrangian of electromagnetic field, linear electromagnetic field, and they found this space-time. They found this space-time for the charged black holes. Is it? Is it working? It is working.
Is it working?
Yeah, it is working. It is all right. Yeah.
Okay.
No, it's pointing. So, and this.
Conduct in order to will it switch or not? I was talking about switching.
Switching.
It will not work because you should.
We just have to plug
this thing should.
Yes.
Yes, it should be.
Right.
Yeah, but I have mouse.
No,
I can do it. Okay. Okay, it's working. So this Schwarzschild black hole is the black hole which has only mass parameter, and the Reisner and the Nordström black holes. Black holes, this which has only mass, which has both parameters, mass and the charge of black hole, and then rotating black hole solution has been obtained by this Kerr with the spin parameter, and rotating, and so we have 3 parameters in black holes which can be physically parameters: mass, spin, and charge parameters. Other parameters which are comes external field, so field via general relativity cannot explain the physical observational phenomena. So actually Einstein's classical theory of gravity, this general relativity is passed through several observational tests. It is well tested, but still we have some questionings which are not answering this observational events. There is a lot of modified and alternative theories of gravity and quantum gravity to be explained. Some quantum effects near the horizon, like this Hawking radiation, and so the problem is this Schwarzschild solution and Rayimbaev-Nordström solution. This black hole solution is in general relativity has some singularity problem. So it is mathematical singularity which is not which cannot be explained as physically in general relativity, and so from this point of view, there are two types of black holes. So black holes are singular black holes and regular black holes. Singular black holes mean there is infinite curvature at the center of black hole, and the regular black hole has finite curvature at the center of black hole. So some alternative or modified gravity, so some regular black hole can be obtained in the frame of alternative and modified gravities, which has some mass plus additional parameter for non-rotating black holes, and this rotating black hole has plus spin parameter. So rotating black hole we have as a Kerr ring singularity problem, this at the equatorial plane, and from this point of view, there are two observational problem. Are the black holes in the universe singular black holes or not? Are regular black holes? And the astrophysical point of view, these black holes are the ending. The gravitational collapse of ending stage of gravitational collapse of main sequence stars, and according to their mass, there are actually 4. I show here 3 astrophysical black holes which can be observed in observations with some signs from the black holes, but there is a primordial black holes which we cannot observe them, but they are hypothetical black holes which is pretending to be the particle of dark matter, and these black holes which has from 3 up to 100 solar mass black holes are stellar mass black holes, which we can meet them, we can observe them in the low mass X-ray binaries or X-ray binaries through the radiation of accretion disk and the quasi-periodic oscillations, and some tests has been obtained in the gravitational wave detection in 2015. I think it was September, and so intermediate mass black holes. So in this range, and some of them observed in the low luminosity active galaxy nuclei, and some of them this distribution of intermediate black holes which has mass near to hundreds solar mass black hole are still under the question. It's still unknown how to observe them, but in future we can get some information about the intermediate black holes using the gravitational wave. Maybe this LISA project can get some valuable information about them. And supermassive black holes, we are believed that they are central part of galaxies, actually active nuclei galaxies, and galaxy centers, and we can observe them through their shadow size, since we have up to now we have only 2 observational data from M87 supermassive black hole and MT7 star and the Sagittarius A star, and most of them observed through their relativistic jets. But in observation, we have some problems that how to measure the black hole parameters. So if they have mass only or spin or charge, it is still a question. So it depends on the black hole model we are testing. And are they still question? Are they regular or singular? This also theoretically also depend on the theoretical approach of analysis and data analysis. And so here according to the No-Hair theorem, we believe that the black hole cannot have own proper magnetic field. So it should be external meaning it can be some binaries in some binary systems. The companion can be white dwarf or neutron star. So black hole can be considered as the immersed and external magnetic field. Maybe the origin of external magnetic field is due to the accretion disk. So according to the calculationists, so stellar mass black hole can have this 100 billion Gauss up to, this is upper limit for magnetic field which generated by the accretion disk, and the supermassive black hole can have only 10,000 Gausses because of the accretion disk far away enough as compared to the stellar mass black holes. And here I will stop. I will show how to test the spacetime around black holes using the quasi-periodic oscillations data and this shadow size. And so actually, what are the quasi-periodic oscillation signals have been found in using this Fourier analysis of noisy data, which is obtained in the accretion disk radiation. And this in accretion disk, we know this it is radiation of accretion disk. It is purely model dependent. For example, for this seek accretion disk or model, all QPO models are quite a lot of physicists, a lot of modes to generate. We can only consider MHD methods in QPO, but all radiation processes in thin accretion disk can be considered using the single particle motion. So for the first time, Rashid Sunyaev has been suggested the possible way to identify the spacetime of Schwarzschild and Kerr black holes. This, according to his model, there is a quasi-periodic oscillation signal should be arise at the ISCO, and we can from this QPO signals we can calculate this ISCO radius, and this ISCO radius shows the black holes is Schwarzschild or Kerr black hole. So for Schwarzschild it is fixed, so 6m, and for Kerr we know, so it depends on its spin, and if it is less than 6m, we can say that this is Kerr, and this is a spin parameter. this all observed QPOs, most of observed QPOs from binary systems has been found in sourced by this neutron stars, but here I show some of black hole sourced QPOs, which has two or one peaks at the higher frequency QPOs, high frequency QPOs and low frequency QPOs, and there is 4 additional signal in the low frequency band, but still the question is it these black hole sources are candidate of black holes. We don't know still, are they black holes or not. We can test them as a candidate, and here some shown this frequency signals in twin peak QPOs. I mean, the data is upper and the lower frequencies we got, and most of them from neutron stars. But here I would like to mention this 4 object which has shown in the line, which has take place in this line 3/2 ratio, so upper and lower luminosity ratio, and here it is here, and we can use this data from this lower and upper luminosity of this QPOs from this microquasars as a black hole candidate. And so mechanism of the quasi-periodic oscillations is connected with the oscillations of test particles. Maybe they are charged particles. They are charged actually because the accretion disk is fully ionized, full with ionized particles. So their oscillations, their oscillations, the radial and the angular Keplerian oscillations can be calculated in the form for non-rotating spacetime, for spherically symmetric, spherically symmetric spacetime. And here the f is a lapse function of spacetime, and for K1 it has the same. It has the following form. I'm not going to details of calculations, but this here I would like to show that these are the frequencies has different value at the same distance, but they have different. But using this difference of frequencies, there are several quasi-periodic oscillations models has been developed using different combinations of Keplerian and radial and this vertical oscillations. For example, in this here I will show some results which are obtained in the frame of this relativistic precession model. This relativistic precession model is shown here. We can see that these orbits are not purely circle. They have some shifts and precession in their orbits, and due to the precession we can see that there is radial oscillations, and the precession claims that this upper luminosity is upper frequency of the QPO using this due to this Keplerian orbits of particles, and the lower can be generated the difference between Keplerian and the radial frequencies. So, and I will show some results where I tested the black holes and some gravity models. For example, spherical symmetric black holes in quantum gravity and modified gravity and the novel theory of 4D Einstein-Gauss-Bonnet gravity, and this is the general form for the spherical symmetric black hole, which can describe it. And in quantum gravity, I show non-commutative inspired black hole model. The black hole is regular and this here the non-commutative parameter is theta, which has critic value, so it cannot be exceed the critic one. And if the theta is larger than theta critic, the black hole turns to some naked singularity. Here in MOG, modified gravity is sometimes called SVT gravity, which is scalar vector tensor gravity. So this general relativity plus some scalar vector tensor field, and here the alpha parameter alpha, which is called MOG parameter, represents the this field effects. Here the a singular black hole solution and the regular black hole solution, depending on the distribution or Lagrangian of this STV scalar vector field, and this solution is regular black hole solution, which is very like this form of the metric is look like this ion Beata Garcia model, because the this Lagrangian is similar to the Lagrangian of nonlinear electrodynamics, which is chosen by the ion Beata Garcia. It has also some critic value. Here it is a singular solution from singular solution in Adias spacetime. Here the the parameter is Adias radius parameter, and some charged black hole solutions, Reinenström, Bardeen, and ion Beata Garcia, regular black hole, I don't know the name of, and the regular black hole second. And this solution is obtained by Babur Tashmatov, our colleague. So it has some degree of nonlinearity. And this, if nonlinearity degree is 3, we fix it as, we call this RBH2 model, and the RBH4 model is for n equal to 4. And these charged black hole has upper limits, has extreme values, and this charge cannot be exceed from this value. And I show some results in the charged black hole in the Einstein-Maxwell scalar black holes. Here some dilation scalar field called dilaton field with the parameter beta and the gamma, which the parameters are corresponding to the scalar field effects. So I would like to show this all my results in Hertz's using this relation with this angular velocities. And here, as I told, this relativistic precession model, first I calculated the Keplerian frequency and the radial frequencies for the upper lower frequencies of quasi-periodic oscillations, and here relations between this is this diagram for upper and lower luminosities. This curve is all possible values of quasi-periodic twin peak quasi-periodic oscillations which can take, and if we consider this quasi-periodic oscillations in observation take place in this, for example, in this point, which lies on the gray curve, we can say it is the Schwarzschild with this value, with this mass. According, so we can calculate this curve using this by fixing this black hole mass, and the black hole, in this case I fix it as a 10 solar mass, black hole mass, and if we change the mass of the black hole, the curve can shift up and down, and still fixing mass, if we if we give some charged black hole with different charge, for example, Rayimbaev charge, Bardian, or we can have some different curves which corresponding to the gravitational effects of black hole charge, and this is for this curve for Bardian black hole. If some black hole, if some QPO appears in this point in observation, we can say or conclude this. This is some. It might be Bardian or some other black holes with corresponding values. There is we can see some degeneracy effects of black hole solutionness and mass of the black hole. So from this point of view, deeper studies in analysis of twin peak quasi-periodic oscillations are most important, because there is degeneracy between the mass and the charge. Here we show black curve as for Kerr black hole. It is the Kerr black hole is 0.8 solar mass, 0.8 m, and it also can give similar gravitational effects on the upper and the lower luminosities, and which may provide the same as black hole charge. Here is some degeneracy effects, some mimicking this black hole spin and the black hole charge. So here in this diagram, this is a similar diagram for NC, so non-commutative black hole, and we show the black this blue dotted line for black hole which has extreme parameter, and we can see from this lower than this point we cannot see any effects between Schwarzschild and the NCI black holes. It means that the black hole, this parameter effects are very, very small, very weak, and we can only see the in higher values of upper and lower frequencies, but it is a difference. It is even small from from this error of an observations. So we can conclude that this range between this gray and the blue lines is in the order of error of observations. So we cannot observe this NCI black holes from this point of view. Quantum effects does not have reasonable or any effects on the QPOs. And here results, similar results in the Schwarzschild-Mach and the regular Mach black holes. We can see that the curves of the S-Mach and Schwarzschild and the regular Machs lies under the Schwarzschild line. We see these lines the curves are positioned at over the. It is on this Mach effects show under the Schwarzschild line, and here also some degeneracy between this Schwarzschild Mach and the regular Mach gravities in this field. But in this field between the red and the blue, we cannot see any degeneracy. But because if some object has positioned in this point, we can exactly say it can be Schwarzschild Mach only. If it is here, it can be or Schwarzschild Mach or regular Mach. It is in this from this point of view, the black hole solutions has also some mimics with different according to the for the different values of alpha, and these are results obtained in the Einstein charged black holes, Einstein Maxwell scalar gravity for the different values of this scalar field parameters beta and gamma, and it is shown that this all curves crosses with the curve of Schwarzschild black hole, and one can say here some at some values of beta and gamma, this even being the black hole being even extreme charge can show the same as show the gravitational effect the same as Schwarzschild black hole. So from this point of view, this external dilaton field can opposite gravitational effect which has charge. So this scalar field compensates the black hole charge gravitational effects. And here we studied this ISCO radius around black hole and the orbits of quasi-periodic oscillations. It means that the QPO the orbitals where QPO occur. So where QPO generates by charged particles, and we use it this 3/2 upper and lower frequency ratio, and we can see the behavior of ISCO and the QPO or radius of QPO and the ISCOs are very similar, and at Q equal to 0. So when the at the Schwarzschild limit Q is equal to 0, ISCO is at 6m, and the QPO orbits at some 6.7. It means there is a distance between ISCO and the QPO 0.7m, and this here this is a relationship between radius of QPOs and this non-commutative parameter. We can see that there is no effects of theta. It is almost constant with the variation of theta, and here this radius of it's possible values of ISCO orbitals, which is between the this ISCO, the QPO orbitals between the ISCO and the QPO orbitals. Here we can see intersection region between for regular and singular black holes. And if we can see that if alpha parameter is less, we cannot distinguish. There is a this degeneracy area for radius for the measurements of radius, and if the parameter are large enough, so close to 1, so it has the degeneracy disappears. On this here the similar results obtained. So for Einstein Maxwell gravity also for charged black holes, we can see all this behavior is the same with the increase of black hole charge. It is the same as ISCO, and as the QPO ratio decreases or close to 1, this QPO orbits come close to ISCO, and from this point of view we can observe, we can measure the ISCO orbit, innermost circular orbitals at the inner edge of the black edge of the accretion disk using the QPO analysis. And if the ratio of upper and lower frequency is close to the 1, and if there is a single particle, this for example, this ratio of upper and the lower frequency is equal to 1, the orbit falls to ISCO, and it means that the ISCO can, single particle, single peak QPO can be generated at ISCO. Twin peak particles are occur and out of ISCO radius. One moment here I would like to mention this line is this line for twin peak QPOs. So it means that under the line there is no QPO can be observed. So this at this point we can only observe a single peak QPO, which it is at ISCO 0 at corresponds to increase infinite orbit. So here this is sorry, this is invisible. So at the horizontal line, this is radius radius of orbit, and we can see that if the radius come close to the 6m, it is 6m is here. The twin peak QPOs, high frequency QPO generators at larger distance, at far orbitals from ISCO, low frequency QPO can be arises. Here some constraints for the microquasar GRS 1950 105 with observational data, and I used here a high square method, and for different this error bar for 1 sigma, 2 sigma, 3 sigma, and this is the best fit where we can find minimizing all quantities, and for different values of this is Reisner, Nordstrom, and ion beta Garcia, and Bardeen black hole, and this 3 type of black holes, and here numerical values of this best fit values we can see. This for example these values, mass values, are different for different charged black hole models, and I get a relation between charge and mass, mean values of charge and mass. Actually, these values are obtained, and I remark these models with red, which are very small, close to the 0.1, and actually astrophysical black holes considered cannot have this large amount of charge. It should be very low, because it is unbelievable how there accumulates such amount of electric charge. So from this point of view, these models, so RBH2 and 3, which is obtained by Waburtash, more astrophysically relevant, and this ion Beata Garcia also can be considered as relevant for astrophysical to be astrophysical black hole. So here, as we told, there is a degeneracy mimicking effects between the charge and the spin of Kerr black holes. So we compare the upper and lower luminosity for charged black hole and the spinning black hole, and the Rayimbaev charge can mimic the spin of Kerr black hole up to these values. Actually, we use the observational data here also, and in providing the same values of this upper and lower frequencies. Here the condition is upper and lower frequency should be the same, but in other observations the mimicking value may be different. For example, in comparison the Kerr and the shadow size of Kerr and the charged black hole, we can get some different value for mimicking values of this spin parameter. And here this two models can show can mimic the black hole spin this up to higher values, close to 0.8. So another test, the black hole spacetime. The way to test black hole spacetime is using the observational data of black hole shadow size. Here the shadow of supermassive black hole M87 star and Sagittarius A star, which has different angular sizes. Actually, there are two different measurements from measurable quantities. This is radius of this circle-shaped shadow, and the distortion parameter, distortion of the shadow from this from circle, and here the distortion parameter, the percentage to show how this is a relation distortion size and the shadow size. And in this test we use rotating charged black holes obtained in the for the Einstein-Gauss-Bonnet theory. The theory is actually this Gauss-Bonnet theory for high dimensions. So in 4 dimension there is some problematics in action, and 3 years ago 3 years ago it's been found by the change of this Gauss-Bonnet coupling parameter from gamma to gamma over 4, and the solution, the problem is solved, and there are several black hole solutions obtained in the frame of Einstein Gauss-Bonnet gravity, and here the rotating solution of the gravity. And we studied this massless particle photon motion using this Hamilton-Jacobi equation, and got celestial coordinates for the spacetime, this spacetime rotating in this form, and we get the shadow of the radius of shadow of the black hole in this form, and we have this observational data from these black holes for shadow size, and we can test it by fixing the shadow size. And here we show the behavior of the shadow, the effects of this shadow black hole charge and the spin of black hole for different values of gamma parameters. So we can see this spin, so it is obtained, the spin of black hole spin can make more increases the distortion parameter, and for here gamma parameter also gives similar effects, the same as spin of Kerr black hole. It also increases it also makes distortion in shadow size. Here the shadow in the different observational angle, and for the different parameters of mass and the charge. And here we use the observational data. This is the angular size of the black hole, and we use this distance between the black hole and the observer, and fixed the angular size, and we get the relationship between the charge of and the mass of and the spin of black holes, which can provide the same black hole shadow size. And we can see that in the frame of general relativity, the spin of M87 black hole, it is near about the 0.9. It is obtained by other observations. Also, it confirms the results are confirms the results, and this positive values of and the negative values of Gauss-Bonnet coupling parameter shifts the relation curve, and this results for Sagittarius A. It is also shown, and at Q equal to 0 limit, the black hole has 0.44 about, and it also confirmed by other studies. And we also studied this shadow of NCI black hole, non-commutative black hole, and we can see it is very small difference, and this observational data show that this error in the observations in the measurements is more than 10%, and this difference is about 4%, and it is smaller than the error of measurements, and we may there is the role of quantum effects is negligible in the black hole shadow and quasi-periodic oscillations. Thank you. It was the last slide.